All right, welcome back, everybody. Today we're going to be doing section 6.4s, and this is where we talk about general logarithmic and exponential functions. This kind of completes, or I mean, it does complete the starred sections. Basically, we're going to round everything off and say what happens when you have an arbitrary base, not just a base of e, or not just a natural logarithm. How do you define these things for any arbitrary base? So let me pull up the slides and we'll get started. All right, let me do this. Okay, nice. All right, so here's the overview. I will say that this lecture should actually be pretty short. There is not too much to cover in it, and a lot of it just follows from what we already got in the previous two sections. So we'll talk about general exponential functions, then we'll finally get the complete laws of exponents, the general laws of exponents. We'll talk about a differentiation formula for general exponentials and logs, an integration formula for general exponentials and logs. I guess just general exponentials. Then we'll get a general logarithmic function, and then we will talk about the number e as a limit. So maybe in the past, in like a pre-calculus course, you saw the number e written as some wild limit of like, something 1 plus 1 over n to the power of n and so on. Now we're going to see how that number is actually equal to that limit. All right, so here's the beginning. We want to define a general exponential function. So let b be a positive number. Generally, we say that b is not equal to 1, but in this case, we can. So we'll just say that b is a positive number. Let x be a real number. Then what we do is we define b to the x as e to the ln of b to the x. Or equivalently, you could just write it as e to the ln of b times x using properties of exponents for e, essentially, right? So this is basically it. How do you actually touch an exponential with a different base? You convert it into one that has e as the base instead, and then you can use everything that we just learned in the previous section. So the function f of x equals b to the x is called the exponential function with base b, as opposed to just the natural exponential function. One thing I haven't addressed, I realized, you may be wondering why we call it the natural exponential and the natural logarithm. And there's a good reason for it, and we're going to see it in this section. It's because when you have the natural exponential, you don't get any extra scaling factors involved. You don't get any extra scaling factors, as we're going to see. Another thing to note, notice that the output of this function is always positive because e to the x is also always positive. All right, this part I'm actually going to skip, but if you would like to see graphs of these general exponential functions, you're more than welcome to just follow this Desmos link, and it'll take you to a Desmos page where you can basically play around with graphs of the exponential functions. The graphs are exactly the same things that you saw in previous classes, so that's why I didn't want to take a bunch of time looking at them right now. Now, because we have this definition for a general base, we now get the laws of exponents for any bases. So if a and b are positive numbers, then we get all these laws of exponents. All these laws of exponents. B to the x plus y is b to the x times b to the y. B to the x minus y is b to the x over b to the y. B to the xy is equal to b to the x times y. And then a times b to the x is equal to a times x. I'm sorry, a to the x times b to the y. And you also get the one for quotients as well. Now, one thing I want to put in here, I remind my students of this in all of my classes because it's one of those errors that everybody makes at every level. But you got to remember that if you have a sum raised to a power, that power does not distribute over the sum. So a plus b to the x is not equal to a to the x times b to the x. No, no, no. No, 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 that's not the case. The way that I always think about it is that these properties of exponents and just exponents in general, they play well with products and quotients, but they don't play well with sums and differences. And the reason for that is just because of the way that logarithms and exponentials are intimately connected. So if you raise a product to a power, then the power distributes over the factors of the product. But if you raise a sum to a power, you're basically dead in the water. The only thing that you can do to address a sum raised to a power is to use the binomial theorem. So the binomial theorem is this. If you have a, oops, we'll use positive integers, a plus b to the n. Maybe some of you might recall that it's actually equal to this. Oh, what is it? A to the n minus k, b to the k. That's actually what it's equal to. So if you have a plus b to the 20, it's not a to the 20 plus b to the 20. Sorry, it's not going to be that. It's going to be a long string with a bunch of terms in it. And the powers are going to change. The powers are going to go up and they're going to go down, and there's going to be coefficients involved given by this right here and Pascal's triangle. So when you come across something like that, it's not so simple, sadly, but just a reminder. All right. The proofs I leave to you. The proofs are just an exercise. I won't do them here. They're pretty much the same as using the log function again. So you basically just use the properties of logarithms and you can get these properties here. Actually, because we have the properties of exponents for a base of e, you can just use those instead. In fact, you do have to use them here now that I think about it, because we haven't defined log base b yet, but we will in just a minute. Okay. Oh yeah, so we also get this differentiation formula. So if you want to take the derivative of b to the x, it's going to be ln of b times b to the x. And actually, maybe this is why, here, let's look at the proof. Here's the proof of it. We're going to use the chain rule. So remember, b to the x by definition is e to the ln of b times x. So now when we differentiate that, we're going to differentiate a chain. So we're going to get the derivative of e to the ln of bx. The derivative of e to the x is itself times the derivative of the inside, which is ln of b times x, is just going to be ln of b. And then remember that e to the ln of b times x is just b to the x. And so that's the result. That's the result. This is actually one of the reasons why we call e the natural exponential function, because when you have a base of e, you end up with this scaling factor being 1. Think about it, right? Let's do this. What if we did the derivative of e to the x? Well, using this formula, it'll be ln of e times e to the x. But ln of e is equal to 1. Ln of e is equal to 1, so you get 1 times e to the x, which equals e to the x. So that's one of the reasons this is the natural exponential. It's the one where there's no additional scalars involved. But if you use any other different base, if you use a base of 2, if you use a base of 10, any other base, and you take the derivative or the integral, you're always going to get a scaling factor of some sort. And the scaling factor is going to be literally the log of that base. Okay, so some properties. These pretty much just follow again from the definition of the exponential function. If b is greater than 1, then ln of b is positive, so its derivative is positive, and so that means that it's going to be strictly increasing. Just like what you would expect, if your base is bigger than 1, you're going to have exponential growth, right? If your base is between 0 and 1, you're going to have exponential decay, a strictly decreasing function. Can also see what the limits are going to be. The limit as x goes to negative infinity is 0, and the limit as x goes to positive infinity is infinity. Or if you have exponential decay, it's different. It's switched, right? So the limit as x goes to negative infinity becomes infinity, and the limit as x goes to positive infinity becomes 0. So stuff that you've seen before. It's all coming out now. All right. Now let's talk about how to differentiate something like this. I want you to think about it for just a minute and then say something out loud about how you would approach it. What do you think you should do to differentiate something like this? Remember, you got to say something out loud. All right, let's do this one together. I'm actually going to show you 2 different approaches, and you can kind of pick which approach you prefer. In my experience, students have a preference, but students vary. And I use both techniques. It just depends on what mood I'm in. Let's do the first technique, which is using logarithmic differentiation. So we can take the log of both sides, and we can rewrite this. Oop, I want my laser. There we go. We can rewrite this as ln of y equals root x times ln of x. And then now we can basically just use the product rule and implicit differentiation. So differentiate both sides of this with respect to x. On the left side, you get 1 over y times dy dx. On the right side, you've got to use the product rule. And so you get that mess. And then solving for dy dx, you get this. And then you can simplify. Remember, we have a formula for y. Y is equal to x to the root x, square root x. So we can just plug that in there and then clean up what was in the parentheses, and that's it. So this is one technique. So this is one technique using logarithmic differentiation. We actually don't need to use this technique to compute this derivative. There is another way. And the way that we do it is we basically just use the definition of a exponential with a different base. So we can rewrite x to the square root of x as e to the power of square root of x times ln of x. That's just using this definition again, right? Remember, b to the x is equal to e to the ln of b times x. That's what's going on. So here we have x to the root x is equal to e to the ln of x, right? In this case, the base is x times the square root of x. So I'm gonna actually say this right for a minute. You should take a moment and just kind of think about what I said and stare at this relationship and see how you can see how this is being used there. So just take a moment, ponder it, look at it, and see how that is coming from that definition. All right, now let's see how the derivative gets computed. Let me clear this out of the way. So if we want to compute the derivative of our original function, x to the square root of x, we're going to take the derivative of this right here. And now we're just going to use the chain rule. So we're just going to use the chain rule in this case, and the product rule gets involved there. But look, when we take the derivative of this, the derivative of e to the x is just itself again. So we get e to the root x ln x because the inside doesn't change. Then we need to do the derivative of the inside, right? So we need to compute the derivative of this, but that's just using the product rule. So just like we saw right over here, you get this, right? When you do the derivative of the inside, you get that. Or when you do the derivative of this, I should say, you get this. So that step is still occurring. That step is still occurring, and we get this after cleaning it up. Then lastly, the very last step, remember e to the root x ln of x is just x to the root x by definition. So we get the same result. Same result. So what I'm going to do now is flash back and forth a couple of times, just so you all can kind of compare the techniques, right? So here you can start by writing this and then solving for dy dx. That's using logarithmic differentiation, or you can just use this definition and the chain rule. Same kind of thing. Your choice. People tend to have a strong opinion about it. I tend to just kind of pick and choose depending on my mood, but it's something that you'll get to think about. So it's kind of fun. Okay, so that's the differentiation formula. Now we also have an integration formula. So if you want to integrate b to the x, where b is an arbitrary positive base, then not equal to 1, I should say. Yeah, not equal to 1, because then ln of 1 is 0. So b cannot be equal to 1 in this case. When you do this, this is actually the result that you get. Just like so. And again, this is one of the reasons why we call e to the x the natural exponential, because if you've got some other base, b to the x, then you always end up with a scaling factor. You always end up with a scaling factor. In this case, it's 1 over log of that base. So integral of b to the x is 1 over ln of that base times b to the x plus c, of course. Plus c, of course. All right, let's prove it. Proving it is actually very easy. We're just going to use u substitution again. Use the substitution rule. We're going to let the first thing we're going to do is we're going to use this definition. Rewrite b to the x as e to the ln of b times x. Then we're going to let u be equal to that product up there. So du becomes ln of b dx, and then we can convert this integral here into this integral here. We just have to scale it by 1 over ln of b, and then the rest all falls out. There we go. So then we're going to get this, but remember e to the u is going to be e to the x ln of b, but e to the x ln of b is just b to the x, and so we get the result. Pretty cute, not too bad. All right, okay, now that we've talked about general exponential functions, we can talk about general logarithmic functions. So now we're going to talk about log base b instead of just log base e, which we actually recover from this right now. So if b is positive and b is not equal to 1, then b to the x is a one-to-one function. Its inverse function is called the logarithmic function with base b, and it's denoted by log base b, log base b. So more specifically, log base b of x is equal to y if and only if b to the y is equal to x. So it's exactly like what you would expect, exactly like what you would want. We also have that log base e of x is equal to ln of x. So that falls out of this definition that we started with way back in 6.2 and then carried through 6.3 and then how we defined the general exponential function in this section. So ln of x is log base e, log base that number. All right. We also have cancellation equations. The cancellation equations are basically the same. Log base b of b to the x gives you a cancellation, and so you end up with x. B to the log base b of x gives you a cancellation, so you just get x. So that's a result now, pretty much the same, but the base is b. Here's a couple graphs of what these general logarithmic functions look like. And again, if you want, you can go to Desmos and you can play around with an interactive example just to see what they look like. But it is the same as what you saw back in pre-calc or in algebra class. That's basically what they look like. So I won't dwell on it too much. The one thing I do want to talk more about is this, the change of base formula. The change of base formula, which again is another reason why E is the natural base. So for any a, b, and x greater than 0, with a and b not equal to 1, this is the general change of base formula. So log base a of x equals log base b of x divided by log base b of a. Or you can rewrite it like this. The idea really with the change of base formula is that sometimes you want to work in a different base, and this formula tells you how to convert between bases. So for example, let's say that you would rather work in base 10, but your data is in base 2, for example. Well, what this formula lets you do is this. Let me pull this up. Let's say you're, what was I doing? Oh yeah. So let's say you're in base 2, but you want to be in base 10. That's what we can do right here. So log base 2 of x is the same as log base 10 of x, but you've got to scale it. You've got to scale it by exactly that factor, log base 10 of 2. So that's really what's happening here. In a very hand-wavy way, this essentially means that log base a of x is equal to log base b of x, except you have to scale log base b of x specifically by log base b of a, 1 over that value. So again, another reason why the natural exponential is nice, because you won't end up with this little scaling factor. And in fact, if you instead just use the natural exponential, so log base e, then this formula becomes this. Log base a of x is just ln of x over ln of a, right? Not bad. If a is equal to e, then everything becomes what you would expect. Log base e of x is ln of x. All right, this note at the bottom, I do want to mention this. You really should memorize this formula. You do need to memorize this formula. You can remember, you can memorize either one of the two. I don't mind which one you memorize. That's totally up to you. The way that I remember it is usually this way. I just remember that log base a of x is equal to log base b of x, but then I've got to divide by log base b of a, the connection between the two bases. All right, let's see, trucking along. Oh, let's differentiate this. So how do you differentiate log base b of x? Let's work on this one together. So we're going to use the change of base formula because we don't know how to differentiate log base b, but we do know how to differentiate log base e, or natural log in other words. So using the change of base formula, we rewrite log base b of x as ln of x over ln of b. Remember, ln of b is just a constant, so we can pull it out through the derivative operator. So pull it out like so, and then we're just taking the derivative of ln of x, but the derivative of ln of x is just 1 over x, and so we get 1 over x times 1 over ln of b, or this. There we go. And again, this is a formula that you could memorize if you want, the derivative of a general base log, but I recommend just memorizing the change of base formula and using the chain rule. It's you know, you don't want to have to memorize everything. You don't want to have to memorize a bunch of little special cases. So try to save yourself some work. Just memorize the change of base formula and use the chain rule. That's frankly it. Just get comfortable with the chain rule. All right. How about this one? Okay, so this one I want you to try on your own. So think about it for a minute. How would you differentiate this? Think about it. Say something about it. What would you do? Got to say something out loud. And then go for it. Try to calculate it yourself, see what you get, and we'll do it together in just a moment. All right, here we go. So first thing is we've got a log base 2. So we're going to have to use the change of base formula, or just remember that formula from the previous example. So here we go. I'm going to employ the change of base formula. Log base 2 of this thing is equal to natural log of that thing, but then you got to scale it. You got to divide it by ln of 2. That's the connection between the two bases. Now when we do the derivative, we're doing the derivative of this instead. Remember, ln of 2 is just a constant, so we can pull it through, or I should say pull it through the derivative operator to get this. And then we can just use the chain rule. So chain rule gives 1 over 2 plus sine x times the derivative of the inside, which is cosine x. And then we can clean things up a little bit and write the final result like this. There we go. Not too bad. Change of base formula and chain rule. That's it. Okay, all right. Now let's talk about the number e as a limit instead. So this is one of those interesting and kind of cute results. Let's see where it comes from. We have all the pieces. So earlier we showed that if your function is the natural log function, then its derivative is 1 over x. So what that means is that f prime of 1 is equal to 1, right? If I plug in 1 right here for x, I get 1. So the derivative at 1 is equal to 1. So if we go all the way back to the beginning of Calc 1 and we write this in terms of the definition of the derivative, we get this result. 1 is equal to this. 1 is equal to this, right? It seems a little funky at first, but look at this for just a minute. This is the difference quotient. That's the difference quotient. Except in this case, the h is x, right? So the h is x. That would be h, like you saw back in Calc 1. Now it's an x instead. There we go. So what is our function? Our function is the natural log function. Natural log of 1 is equal to 0. So we just get ln of 1 plus x over x, right? And now here's where we get to be a little bit clever. So this is kind of cute. We can write this as 1 over x times ln of 1 plus x, just through some algebraic massage, right? But what does this get us? Well, look, remember, this is basically multiplying a natural log function. So the properties of logarithms, in particular the power rule, means that we can throw this factor in as an exponent, and so we get this, ln of 1 plus x to the power of 1 over x. And now we're taking that limit. So it seems kind of funky. It seems kind of funky, but that's the limit that we have right now. All right, now we're going to be clever again. We're going to exponentiate both sides, but we're going to use a base of e. All right, so we're going to basically e both sides like this. We're going to e both sides. Well, if we do e to the 1, that's just equal to e. And then e to this limit is just e to that limit. So it looks kind of gross, but something's going to clean up in just a second here. All right. Now, remember the exponential function is continuous. We were talking about that before. It's continuous, so by the definition of continuity, we can move the limit operator inside or outside the argument of the function. And then we can use the cancellation equations after that. So what I'm really trying to say is that to go from this step to this step, we're using the fact that the natural exponential function is continuous. So we can basically pull the limit operator out to here instead, out to here. All right, now what we get is this. Now we get that e is equal to this limit right here. So the limit as x goes to 0 of 1 plus x to the 1 over x is equal to e. Interesting, interesting. Thus, we get this. Just writing it in a box form. But now we can also manipulate this a little bit. We can tweak it a little bit. If we let n be equal to 1 over x, and using the fact that the limit as x approaches 0 from the right of 1 over x is the same as the limit as n approaches positive infinity of n, we can rewrite the number as this limit instead. Boom. So that's a way of writing e as a limit instead. If you're wondering how we got the 1 over n, it's from this relationship here. This implies that x equals 1 over n. So if you replace this x with 1 over n, you get that. And then if you replace this 1 over x with n, you get that. So that's really what's happening. We're converting it to a limit in terms of n instead of x in this case. There we go. So altogether, we get this. Here's e written as a limit in two equivalent ways. This is actually where the formula for continuously compounded interest comes from. And we're going to derive that complete formula in the next section. But if you feel like this structure looks familiar, it's because it's part of the compound interest formula. The compound interest formula is this, but tweaked a little bit. And then when you do it continuously, when you compound continuously, the formula involves e. Why does the formula involve e? Because e is this limit, as we just showed. So that's a little bit of a flash forward to what we're going to talk about in the next section. But for now, let's play. So we're going to do an activity related to this one, 6.4 star. This also ends the starred sections. So now we're going to go back and keep track with the book using just the regular sections instead. So yep, once again, thank you for bearing with me. Thank you all for listening. I look forward to seeing you again, and I will see you next time to talk about, I think it's exponential growth and decay. 6.5, yeah. All right, so have a good one, and I'll see you next time.